Hey class, this is going to be your 6.1 video. Chapter 6 is things that we don't normally include in the ECC curriculum, but these are the two sections that I wanted to make sure you had if you were transferring to SMT. So the idea here is that we are going to find volumes of things using integrals. That's the basics of 6.1 and 6.2. And the first and possibly easiest case I've sketched out here, if you have some solid where you have a height along, it's easiest to think of it along the x-axis because that's how we've been integrating, and that at each x you have some sort of cross-sectional area A of x. Then the volume of this region, this solid, is the integral as x goes from a to b of a of x dx. And that's just, that's based on the same idea as if you have a cylinder or any sort of a regular shape, then the area of the base times the height is the volume. And it can be, like I said, a right circular cylinder. It could be some sort of a prism. All these shapes with a regular cross section, where the cross sections are always the same as you take slices along, will have volume equal to their area times their height. And then we take that out of context for our general regions, and instead of just multiplying, we do an integral along the direction of the height and then of the cross-sectional area. So if the area is a constant, then we get this back exactly. So let's call this 0, and let's say that's h. And so the integral from 0 to h of a constant area, dx, is just going to be a h, like those. What else here do you need to know for that? I think that's probably good for that. So that formula comes up from time to time. One of the things that we like to use this formula for, or this idea, is for something that we call a surface of revolution, or a solid, I guess, of revolution in this case, because we're talking about the whole solid. And so if my region were to look something like this, again, I'm going to take this to be the x-axis, but I'm going to kind of ignore the y-axis. So if I take something like this parabolic curve and rotate it around the x-axis, so I start with this curve and then I rotate it all the way around, then that would be a solid of revolution. And if I wanted to find the area of this thing, well, I'm sorry, the volume of this thing, that's definitely fits the pattern. I can use cross sections. I can take the integral from a to b of a of x dx, but my cross-sectional area is going to be pretty easy to figure because it's a circle, since it's a surface of, or a solid of revolution. So since I just revolve it around that x-axis there, a of x for any given x is going to be equal to, for this one, let's be nice to ourselves. Let's assume a equals 0, and then just b equals b. That'll just make this formula a little bit easier. And so let's assume, and it's not quite right for this, let's give that as y equals the square root of x. That's pretty close to that. So well, how about that? So y equals the square root of x is that curve. So then I said we wouldn't worry about the y-axis, but I guess I'll draw it in. So in that case, this height is your radius, and that for any given x is the square root of x. So the area of a circle is pi r squared, but r in this case is actually y. So this is just pi x when I plug in square root of x for my radius. So the volume here becomes the integral from 0 to b of pi x dx. So that's the integral of pi x squared over 2 as x goes from 0 to b. So that's going to be pi b squared over 2. Let's see. In general, this formula is on the top of page 371. We can say that v equals the integral from a to b of a of x dx. And this is the integral as x goes from a to b. But then we can replace a of x with our pi r squared. So we'll have pi times our radius function of x squared dx. What we're doing here is assuming that each of our cross sections is a disk, so long as our surface gives that, then the radius of that disk is kind of the height function of the curve that would generate that solid. And this is called, by many books, the disk method. That's really close to the one I just did. Ooh, here we go. This is example 5 from that same page. The circle x squared plus y squared equals a squared is rotated about the x-axis to generate a sphere. Find its volume. So let's sketch it out real quick. If I start with a sketch in the xy plane and I draw my circle radius a, then what I'm doing here is I'm rotating that around the x-axis so I get a sphere radius a. And so in this case I know that x goes between negative a, and my height function here is what happens when I solve this for y. I can take the positive one there. I can say y equals the square root of a squared minus x squared is my height function, or properly in terms of our method we should call that r of x. So then a of x is just equal to pi times r of x squared, so that's pi times a squared minus x squared. And our volume is the integral from minus a to a of pi times little a squared minus x squared dx. If we go ahead and do that integral, we get pi a squared x minus pi x cubed over 3 as x goes from negative a to a. That's going to be, see how carefully I can do this, pi a, this is for positive a, pi a cubed minus pi a cubed over 3 minus pi a cubed, but it's negative, and so will the next one be, so let me make that positive, minus pi a cubed over 3. Those things are actually the same. As a matter of fact, this is from one of those places where if I had realized symmetry ahead of time, I could have saved myself a little trouble and said that this was equal to 2 times the integral from 0 to a of pi a squared minus x squared dx. You see, we get the piling up here. So that's going to be 2 pi a cubed minus 2 pi over 3 a cubed. 2 minus 2/3 is 4/3. So 4/3 pi a cubed, which is, you can verify it, I think it's in our books, in the front or back of our book somewhere, the formula for the volume of a sphere. These don't have to run in the x direction, so this is example 7, where we rotate the curve x equals 2 over y around the y-axis. Now, that is not the around symbol, but I think it's a missed opportunity, so I use the at symbol for about or around an axis. This is not standard notation, but I think it's pretty intuitive what I mean. So I'm going to rotate this curve around the y-axis, and so that curve is going to look something like this. There's more to it. Let's see. This is for y between 1 and 4, though. So here's y equals 1, there's y equals 4, we'll say. And when I rotate that around the y-axis, I get this little planetarium sort of looking shape almost, or maybe a volcano. Let's call it a volcano today. So this volume is the integral now as y goes from 1 to 4, and it's still pi times my radius squared, but my radius is now a function of y instead of x, and I want to integrate with respect to y. So my radius is just this distance, which was already given to me because it's my x distance to the curve. So if it's solved for x, it's really easy to just plug in just like before. If it happened to be solved for y when you got started, just solve it for x. So this is going to be the integral from 1 to 4 of pi times 4 over y squared dy. And so that's equal to 4 pi. Let's see, integrate that, we get negative 1 over y. And we want to evaluate that as y goes from 1 to 4. So that's equal to, let's see, is that negative pi when y is 4 plus, minus a negative really, 4 pi when y is 1, which is 3 pi. Let me quickly show you, because one of the people sometimes don't stop to think about these. What if I had rotated this curve around? I keep doing this because I'm thinking about graphing it in 3 dimensions. You don't have to worry about that guy right there. What if I had taken this same thing as y goes from 1 to 4? This is, I just bumped it out a little. It's not as good of a graph as the previous one, but go with it. So y goes from 1, maybe more like this, to 4. What if I rotated that around the x-axis? Like so. Gives a similar looking shape, but it's more squat and it's bigger. But now I need to know this function, my height function, if you will. So I need to solve that for y. So that's y equals 2 over y. But my limits need to change too, because I need to set this one up as an integral for x. And so when y equals 1, that should be 2 over x. When y equals 1, x equals 2. And when y equals 4, x equals 1/2. Does that look right? 2 over 1/2 is 4. 2 over 2 is 1. Looks good to me. So then that volume would be the integral from 1/2 to 2 of pi times 2 over x squared dx. Just writing it out here, 1/2 to 2, so that'd be pi times 4 again over x squared. So the integration is going to be the same, right? We get 4 pi times negative 1 over x as x goes from 1/2 to 2. So then when x is 2, that's going to be negative 2 pi, right? Plus when x is 1/2, that's going to be 8 pi. So we actually get a volume in this case of 6 pi. So I just wanted to show you that these would be different if you rotated around a different axis. So it is important to pay attention to that instruction of which way. Now, that's the disk method. There is a method that's often called the washer method. We're still relying on the idea that the volume is the integral from a to b of a of x dx. But the area of a washer is one disk minus another disk, and that's really the only difference. So using the washer method, our cross-sectional areas would look like the volume would be the integral from a to b, but then our area is pi times our cross-sectional area here is pi times the outer radius squared. I'm going to use, let me do what the book does. They're going to use cap r for this. Cap r of x squared minus pi times little r of x squared for the inner or smaller radius. And you can factor that out and just get pi times big R of x squared minus little r of x squared dx. So what would that look like? Well, example 9 is a good example of this. So the region bounded by y equals x squared plus 1 and y equals negative x plus 3 is revolved about the x-axis to generate a solid. We're going to find the volume in a second. Let's just draw it out to start with. So we're going to revolve it around the x-axis. It's going to be easiest for us if we go ahead and graph what this looks like. So x squared plus 1 we know looks something like that. Y equals negative x plus 3, 3 is going to look something like that, which means we're going to need to go up a little further to catch that guy. So this goes to the left of the y-axis over here, and it stops over here, and we don't know what these points are, but this is the region that's bounded. And then we're going to take, and we're going to see if I can sketch that reasonably well. We're going to rotate this region around. It's not this inside part, it's the outside part. That is not a great picture, and I recognize that, but keep in mind that it's this shaded region that got rotated around, not this inner guy. So this is my little r, and this is my big R. So the cross-sectional area here, A of x, equals pi times big R squared of x. I'm going to use that notation there instead of all those extra parentheses, minus little r squared of x. That's just like when we say sine squared, and we mean sine of x quantity squared. All right, so big R is what? Well, it's our line. So this is equal to pi times, I'm going to call it 3 minus x. You can call it negative x plus 3 if you'd like, squared. And then little r is what? Well, that's our parabola. So that is x squared plus 1 squared. And I recommend you go ahead and multiply this out, FOIL it out, combine like terms before you bother to put it in the integral. It'll just make your life a little easier. Now I'm not going to multiply out the pi, just the inside part. So let's see, that's going to be x squared minus 6x plus 9 minus x to the fourth minus 2x squared minus 1. So I get pi times negative x to the fourth minus 2x squared minus 6x plus 8. That's what I'm going to integrate. So my volume here of this is the integral from, oh, we didn't ever find these points. We need to find our limits. The way we find our limits is actually to find the intersections of these two curves. So we set x squared plus 1 equal to negative x plus 3, because where the y's are equal. And then we figure out what x values, let those y's be equal. So that's x squared plus x minus 2 equals 0, x plus 2, x minus 1 equals 0. So x is equal to negative 2 or 1. Those are our limits. So x is going to go from negative 2 to 1. A of x dx, where in our case we know a of x is, we'll put the pi out front, a pi times negative x to the fourth minus 2x squared minus 6x plus 8 dx. Some easy polynomial integration later. We get, and substitution, we're going to get 117 pi over 5. So that is the washer method. So we have 3 methods for finding volumes. One is the most general method. That is this idea that the volume of something is the area of the cross-section integrated across its height. Height loosely defined as including when it's laying sideways. Then we have the disk method if the cross-sections are all circles, and the washer method if the cross-sections are basically circles with holes in them. That's it for 6.1, guys. Good luck.